So this is your MYP1 Advanced Chemistry. So we're going to start off with modern atomic theory, which says that all matter is composed of atoms, which is very true. When we talked about organization of life, atom was one of the smaller ones that we had. Atoms can't be subdivided, created, or destroyed in ordinary chemical reactions, meaning that we can do it. It just has to be done in a very expensive lab because they're very reactive, so dangerous things can happen. That's why the next bullet says it is possible with nuclear reactions. So we have nuclear power plants, we have nuclear labs, and that's what they do. They go around, they split those things that normally we cannot do in a everyday natural setting. Atoms of an element have a mass that is unique to that specific element. So you'll see when you see the periodic table that there's an atomic mass. That is how much that atom weighs, or that element weighs, and that comes from the neutrons and the protons that are inside of the atom itself. Atoms of any one element have properties that are different from other elements, and that's what makes them so special. Okay, that's why certain things need to be bonded with those specific elements. Atoms are neutral, they have the same amount of protons and the exact same amount of electrons. Neutrons have no charge whatsoever. So these are found in the nucleus of the atom. The mass of an atom, like I said before, is made up of the protons and the neutrons, and the nucleus is small and dense. It's at the very center of the atom. So the number of protons in the nucleus is equal to the atomic number. So for instance, in this example, we have hydrogen. So hydrogen is number 1. That means it has 1 proton. In its neutral form, it would also have 1 electron. You have your chemical symbol there, and then your relative atomic mass. So 1.01, you know that you have 1 proton, so that 0.01 has to be a neutron that weighs 0.01, because that's how you get your atomic mass. So remember, if it's neutral, okay, your atomic number will give you your protons. That means that you have the same number of electrons when it's neutral. So for instance, carbon is 6. So 6 protons are in carbon. So you'll have 6 protons or 6 electrons in carbon as well. So here's to explain the atomic mass. Here's another graphic. Like I said before, in this one we have 6 protons and 6 neutrons. So 6 plus 6 is 12. That gives us the atomic mass of 12. All right. If you were to go ahead and do it on the phosphorus over here on the right hand side, you would see it says 30.973762. You would subtract that from 15 because that's your atomic number, which equals your protons. So when you subtracted that, the difference would end up being how many neutrons you actually have inside of the atom. Now, there are different models on how to build an atom or how to construct the atom and how it looks. So Niels Bohr imagined that electrons orbited the nucleus like planets orbiting around the sun. So that's normally the picture that you guys see most often when you're looking up atoms. So you can see you have all your protons and neutrons in the middle, and then you have these rings with the electrons on the outside. The first ring is always going to have 2 electrons, and then the next ring ends up with more than that. There's like a rule of octets, and you'll see that in a second. So your first level, these are how many electrons each level can hold. So like we were saying just now, your first level can only hold 2 electrons. Your second level can hold 8 electrons. And your third level can hold 18 electrons. And then your fourth level can hold 32 if it needs to. And those are more for like the numbers at the very, very end of the periodic table when you have very high atomic numbers. For the most part, the ones you're going to be dealing with are rather small. So you're talking about maybe you're going to be dealing with, you might be dealing with the third level, but for the most part, it's really going to be the first and the second level. So an electron orbital is like what you saw before where the energy level is. It's a region within the energy level where there's a probability of finding an electron. And orbital shapes are defined as the surface that contains 90% of the total electron possibility. So that shape, and you'll see all the different shapes, means that there is a 90% chance that within that shape you're going to find the electrons there. The s orbital has a spherical shape, the p orbitals are dumbbell shaped, and the d orbitals are a double dumbbell shape. Okay, so just if you go before it, it'll look like a ball, and then for the sphere, so you have the sphere on the first one, the second one kind of looks like a dumbbell, and then you have the double dumbbell, but you'll see those. Looking at this chart, okay, so your first orbital level is 1s, and then you go 2s, and then 2p, right, because you have two sublevels, and then this just means like how they look at it through the periodic table, which you're going to see how that works, so that way this chart will make sense. So the maximum number in your first principal energy level is 2, the maximum in your second one is 8, and that's because you have one orbital with 2, and then you have the other orbital with that can hold 2 apiece. Then you have 3, which will hold a maximum number of 18. Okay, and you have 4, which the maximum is 32. So looking at it, okay, you have your S's are in purple, your P's are in green, D's in red, and F is in blue. So if you wanted to say, I want to find the energy levels for carbon, you would say you would have 1s1 because it's on the left hand side. You start where 1s is. You get 1s2, that's our energy level. Then you would go down to the 2s1, and then you go to 2p and count however many. You'd have 2s2, so then you go down to wherever you have the 2p. It would be like 1, 2, 3, 4. So you might have 2p4, 2p3, and that would tell you the energy, which orbital was in. So looking at your periodic table, the elements, if you were going to practice that, if you, like I said, went for carbon, we would consider hydrogen and helium. That's our 1s level, so 1s2. And then you went down and you saw 2 at lithium, so 2s2. And then when you see boron, that would be 2p. Carbon is the second one, so 2p2. Okay, if it was fluorine, you would have to count out, and then you'd be 2p5. So that's how you would do it. But this is your periodic table of the elements. This one's a good one for you guys to use because it shows you what your nonmetals are and all the different groups that you have, and that way you would be able to figure out whether it's a metal or a metalloid, transition metals. It helps when you're learning the different ions and covalent bonds and stuff like that. So when you look at the periodic table, the groups are arranged in columns and the periods are arranged in rows. So if you see, if they're talking about a group or a family, you're going to go down the column. That means that they have the same kind of characteristics as every other element in that column. So hydrogen, lithium, sodium, those all, they're going to have very similar as far as atomic charges and stuff like that, because we're going to get into ions and covalent bonds in a second. So your alkali metals were in the very first group. They are in group 1. They all have one valence electron, so that a valence electron is a electron on the outermost shell that we've been learning about. And they are never found pure in nature because they're too reactive. So they normally need to have one or more of them, or they have to bond in a different way because of the fact that they have that one valence electron just floating around, and they want to have at least 2. As you go down the group, the reactivity increases. So as you go down that column, they're going to become more and more and more reactive. Alkaline earth metals are in the second group, okay, and they're less reactive because they have more valence electrons. They are the second group in the periodic table, and they're not found pure in nature because they, again, are also too reactive. These are also metals. So the properties of metals, they are good conductors of heat and electricity. They're malleable, which means that they can be moved around. They're ductile, they have high tensile strength, and they have luster to them because they're the metals, so they have that shiny property. Transition metals are all the metals in the middle section of the periodic table, which include gold and silver, and those, they each have their own kind of properties. They're not exactly like the metals from your first two groups. They're kind of slightly different. Here you'll have more isotopes and stuff like that that go with it. And then afterwards we have properties of metalloids. Those are going to be metals and nonmetals. They're more brittle than metals, but less brittle than nonmetals, and they're semiconductors of electricity. Then we have the nonmetals, which are poor conductors of electricity. They're very brittle. Most of them are gases at room temperature, and a good example of this is going to be carbon. We're going to finish up on this one, and then you'll have a second video for the rest of your PowerPoint.